3 independent research track, sequential will take 12 seconds. Parallel might take 8. The parallel pattern trades the strict ordering for concurrent speed. And you're about to see exactly how fan out and fan in works. Plus, there is one constraint that I would like to make sure we remember when we process parallelly. Let's understand using a very simple example. You send a market research request, which requires cloud computing trend to be analyzed, competitor positioning, and developer sentiment to be analyzed. Totally 3 independent research tasks. Ticked off from first query. The parallel agent fire all 3 branches at once. Nobody waits for anybody. They all are running concurrently. So your total latency is just the slowest branch, not the sum of all 3. The trend analyst zeroed on market trajectory. It figured out adoption rates, growth segments, emerging technology, and it types everything, whatever it finds, into a session state under, let's say, variable called trend output. At the exact same time, the competitor analyst is mapping the competitive landscape, market share, features, pricing. It doesn't need anything from the trend branches, completely independent. And the sentiment analyst is evaluating developer adoption signals, such as like community activity, satisfaction, pain point. All the 3 branches and the prompts are running at once. Now here is the fan-in. The sequential agent read all 3 output keys from stress and state, which you mentioned as trend output, competitor output, and sentiment output, and synthesize them into the one report. The parallel agent will give you the speed. The sequential will give you the merge. The final report pulls insight from all 3 tracks, combined, cross-reference, structured, and then total latency. The slowest branch plus merge. With 3 branches are about take 4 seconds. That's 8 seconds instead of the 12 if we process sequential. It's a very simple math. 3 branches, 4 seconds each, 12 seconds for sequential, and this is the slowest branch plus merge, which is 8 seconds for the parallel. Now bumped with the 5 branches, and the saving would be even more. So why go parallel? Speed? Your total time is just the slowest branch, not the sum. And the scalability, you can virtually scale to any segment, any label. And understanding the latency is the slowest branch plus merge. That's always going to be the static part. And more importantly, the isolation. The one branch failing does not take other branches down. That's one of the core benefits of parallel. And here's the one rule which I think parallel processing cannot break. And that is all the branches must be independent. If branch B depends somehow on a branch A, then you don't have a parallel problem. You got a sequential dependency wearing a parallel costume. Beyond that, watch out for resource contention. Also, rate-limited APIs could be difficult if the large number of the branches or the significant number of the branches has been fanned out in a very quick succession. Merge complexity is also the area that parallel processing should look for. And especially when the output conflict, how the conflict resolution should take place, and also the debugging is likely or comparatively more complex than sequential processing. But despite that, the parallel has its own value and merit. So now let's see in action with the Visual Studio Code and see how it works. So I'm going to move to Visual Studio Code and let's see. I already got the server up and running, and all I'm going to do is I'm going to tear out the prompt for the client, and I'm just going to fire the client itself. We've got an Ollama LLM, micro LLM running, and we are just continuing with our example patterns, which is the trip planner. They're trying to plan a trip with a concert, museum, and restaurant finder, and they're using A2A protocol to connect with all three agents. There are three agents and orchestrator running inside a server, and it's now synthesizing. So let's see. Excellent. So we did the San Francisco one, if I'm not wrong. Yes, the San Francisco one is here, and it defined our itinerary based on what we asked. We asked for restaurant, which is dinner and lunches, and we asked for museum, and we also asked for concert, and it did pretty well. And the same thing it did for Tokyo National Museum. So we also asked for another query. Say I'm going for Tokyo, suggest me something extra. So it works pretty much as anticipated. That's a parallel pattern. Pan out two independent branches, fan in with the merger, and cut your latency by a third or more. Together with single and sequential, now you got three building blocks that covers most real-world agent system before you ever need coordinators and do. Just a one pro tip before I conclude. In my experience, most of real-world agentic AI are within the realms of single agent, parallel agent, and sequential agent. It provides you the complete DAG architecture. And there are only very specialized use cases where coordinators and loops are required. The more simpler the solution is, the better for manageability and overall performance of AI system. Unless we need, there is no point extending and living with the complex AI architecture, which generally tend to be more difficult to maintain and manage for desirable outcome in future. That's my overall observation in couple of last years since I'm working with agentic AI. So thank you very much for tuning in, and I expect to see you in next videos. Please make sure you subscribe and also save the playlist, because we're gonna upload more agentic AI patterns video in this particular playlist. Thank you very much, and I'll see you in the next video.